So we talked a lot about systems with rational Laplace transform. And why is that, right? So the reason is that it actually occurs quite often. In particular, if we're looking at systems that can be described by linear constant coefficient differential equations, then actually the Laplace transform for this type of system all have a rational Laplace transform. Okay? And you can infer this simply from the convolution property. Right? So this is similar to the Fourier transform as well. Right? So by the convolution property, you know that the Laplace transform of the output is the multiplication of the Laplace transform of the filter times the Laplace transform of the input. Okay? So if you move x to the other side, right, you get the Laplace transform of the filter. And you will see that it is the ratio of two polynomials, one corresponding to the input and one corresponding to the output. Okay? So we can look at a couple of examples. So here we have a simple example. So if we apply this here, okay? So first of all, right, the derivative of y has a Laplace transform that is s times y of s plus 3y of s equal to x of s. Okay? So this is the Laplace transform of y, and this is the Laplace transform of x. Okay? And then to find the system function, you simply move x to this side and this s plus 3 to the other side. Okay? So the system function is y of s over x of s, which is 1 over s plus 3. Okay? Now, this only gives you the algebraic expression, okay? But the algebraic expression is not enough. Okay? So the algebraic expression is not enough for us to completely characterize the system. We further need to know what is the region of convergence. Okay? Now, suppose we assume that the system is causal. Okay? So if the system is causal, then the ROC must be the right half plane to the right of the pole, which is -3 in this case. Okay? So then the ROC is the right half plane to the right of -3. Okay? So this corresponds to an impulse response that is equal to e to the minus 3t u of t. Right. Okay. Now let's look at a more general case. Okay. So suppose we have this system given here, described by this linear constant coefficient differential equation. So similar to before, we can start out by taking the Fourier transform, the Laplace transform on both sides. And that will give us summation k from 0 to n, ak s to the power k of y of s equal to summation ck s to the power k x of s. Okay? So then we can find the Laplace transform of the system, right? The system function or transfer function as the ratio of y of s over x of s. And this is equal to summation bksk, k from 0 to m, over summation ak sk, k from 0 to n. Okay? So from this general case, you can see that indeed, for a system described by linear constant coefficient differential equations, the system function or the transfer function is always rational. Okay? And the zeros will correspond to the polynomial in the numerator, and the poles will correspond to the polynomial in the denominator, right? So the system function specified by the, this differential equation is rational with zeros that are the solutions of the numerator. I think this should be the other way around, right? Zeros corresponding to this, poles corresponding to this. Okay? So zeros corresponding to this, and poles corresponding to this. Okay. Okay. Now, previously, we were accustomed to giving, the condition of initial rest when solving the system of linear equations. So when you are given the condition of initial rest, you can show that the system must be causal, and therefore, the region of convergence of this should be the right half plane, and because this is rational, it should be to the right of the rightmost pole. Okay? Okay. So we have one last example, but this is pretty straightforward, right? All the operations are the same. Okay. So here we have just one more example. So what you do with this is the same as before, right? You can take the Laplace transform on both sides to obtain a ratio of y of s over x of s. Okay. So if you do that, you can find that the transfer function or system function is 1 over LC over S squared plus R over LS plus 1 over LC. Okay? Now you have a second order polynomial in a denominator, so you know that you should have two poles. Okay? So if you find the zeros of this denominator, then you know that the poles are at s equal to minus r over L plus minus square root r square over L square minus 4 over LC over 2. Okay. So this system, right, describes this RLC circuit here, right? Describes the input-output of the RLC circuit here, okay? Input being the voltage source and the output being the voltage across the capacitor, right? Now, assuming that R, L, and C are all positive, is this system causal or not? Okay. I'm sorry, I should say, is this system stable or not, right? Assuming that it is causal. Okay. So suppose we, as before, we give the condition of initial rest. So by the condition of initial rest, we will know that the system is causal. But is this system stable or not? Okay. So suppose that by the condition of initial rest, the system is causal. Okay? And the question is the system stable? Okay. Yeah. So how many of you think it's stable? Okay. So how many of you think it's not stable? It is not stable. No. Okay. So it is stable because the poles are negative. Okay. So it is stable because the pole is negative. Okay. So you have poles that are negative, right, in the left half of the S-plane, and therefore, the ROC would include the J omega axis. Okay. So yes, since the ROC includes the J omega axis. Okay. 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 So this is all I want to talk about for chapter 9. Okay, the Laplace transform. Okay. So I think the most important thing that you should understand about the Laplace transform is that it is a generalization of the Fourier transform, trying to address, deal with signals that may not necessarily be absolutely integrable by itself. Okay. So we gave this example at the very beginning. Oops. Okay. So we gave this example at the very beginning, right? So suppose you're taking the Laplace transform of the signal x of t at the point s equal to sigma plus j omega, okay? So if you plug in s equal to sigma plus j omega, right, you can show that the Laplace transform is actually just the Fourier transform of the original signal multiplied by this e to the minus sigma t, okay? So this sigma is a real value. If sigma is greater than 0, it is decaying to the right. If it is less than 0, then it's decaying to the left, okay? So this exponential can be used to suppress part of x of t that is growing undesirably, okay? So for example, suppose you have this x of t that is growing to the right, then you can multiply it by this decaying exponential that suppresses this part of the signal, right? And by choosing sigma large enough, you can suppress this part to the point where it becomes absolutely integrable, okay? And in that case, you can perform the Fourier transform, or overall the Laplace transform. Okay, so this is really the essence of the Laplace transform. So then the question is, how large or how small should this sigma be in order for you to obtain a absolutely integrable signal? Okay, so that corresponds to the choice of the region of convergence. Okay, so for certain signals growing this way, right, you need sigma to be, at least as large as a certain value. So in that case, the region of convergence will be to the right. Okay, so if you have a signal that is growing to the left, then you would have a region of convergence probably, going to the left, right? So region of convergence really corresponds to, how large or how small we need this sigma to be in order to suppress the growing part of the original signal x of t. Okay. All right. So we can extend this concept to discrete time Fourier transforms as well. Okay, so this chapter 10 is about the Z transform. The relation between the Z transform and the discrete time Fourier transform is the same as the Laplace transform with the continuous time Fourier transform. Okay, so the entire structure of this chapter is essentially the same as chapter 9. All right. So if you recall, when we introduced the discrete time Fourier transform, one of the main motivations for studying the discrete time transform is because the signals of this type, right? Suppose we input a signal that is z to the power n, right? Signals of this type we discover is an eigenfunction of any linear time invariant system. So what this means is that if we plug in the input that is z to the power n inside a linear time invariant system, we will get an output that is also the same function as the input, just scaled by this h of z. And it just so happens that h of z here is the summation of h of k times z to the minus k, which is the Laplace transform of h. Okay? Now, previously, when we talked about discrete time Fourier transforms, we focused on the case where z is equal to e to the j omega. Okay? So if you plug, okay, so here we have, here we have a general, z transform, or in the case of x, right, this is the z transform of x. But if we focus on the case where z is equal to e to the j omega, then what we get is the discrete time Fourier transform, right, which is this. Okay? Right. So again, the discrete time Fourier transform is a special case of the Z transform by choosing Z equal to e to the j omega. Okay. Now, what is the advantage of considering a more general Z other than this e to the j omega? Okay. Now, suppose that we choose to view this Z as r times e to the j omega. Okay, so suppose we choose Z to be this magnitude r times e to the j omega. So this is a polar expression for any complex value, right? So if we plug this into the Z transform expression, right, we get a summation of xn times r times e to the j omega, the whole thing to the power minus n. And then if you group r to the minus n together with xn, then what you have here is exactly the discrete time Fourier transform of this new function here. Okay? So what I'm saying here is that the Z transform is nothing more than the Fourier transform of the function xn times r to the minus n. And the same advantage as before applies here, because this r to the minus n helps us suppress parts of xn that is growing undesirably. Okay. For example, if you choose r to be greater than 1, then as n, as n increases to infinity, this r to the minus n decays, right? Becomes smaller and smaller, right? Now, if you choose r to be less than 1, right, between 0 and 1, then as n becomes negative, right, this thing will decay to the left, okay? So for r that is greater than 1, you suppress part of xn to the right, and for r that is between 0 and 1, you suppress signals to the left, okay? So even though the original x of n may not be absolutely summable, which is the requirement for Fourier transform to exist, xn times r to the minus n may be absolutely summable, right? Even though xn by itself is not. Okay, so this allows us to handle a larger class of signals. Okay? All right. So if you compare with the previous chapter, right, in the continuous case, right, which we talked about in the previous chapter, the Laplace transform reduces to the Fourier transform when s is equal to j omega, which corresponds to the real, the line corresponding to the real part of s equal to 0, which is the j omega axis, right? This j omega axis. Okay. So in the continuous case, the Laplace transform reduces to the Fourier transform when s is equal to j omega, which is the j omega axis. But in discrete time, the Z transform reduces to the Fourier transform when Z is equal to e to the j omega. And Z equal to e to the j omega actually corresponds to a circle, right? Corresponds to a circle with magnitude equal to 1, okay? So in the discrete time case, the Fourier transform instead corresponds to this circle, okay, with magnitude 1. So this corresponds to the unit circle centered at the origin.